Hello everyone. Let's continue with the SPICE analysis. We did the SPICE simulations for a device where PMOS was 2.5 times greater than NMOS, and basically the width of the PMOS was 0.9375, and this is 2.5 times of your NMOS. So we did that for a purpose to show the difference in the SPICE characteristics. So we'll try to analyze this particular SPICE waveform. For that, what we'll do, let us keep these two waveforms side by side. So we have in this side we will have the SPICE waveform for Wn equal to Wp, where your PMOS and MOS sizes were exactly the same, and it is 0.375 is the width and the length is 0.25. That's constant across both the analysis that we did. So in this case, W by L ratio of the NMOS is equal to W by L ratio of the PMOS, and that's equal to 1.5. Okay, and the next is the scenario where your Wn was kept to be same 0.375, just as the previous experiment. Your Wp was 2.5 times of Wn, and your NMOS PMOS length, channel length, was kept to be same. So in this case, W by L ratio of PMOS was 1.5. In this case, we increase the W by L ratio 2.5 times of 1.5, which is 3.75. Okay, you can just do this divided by this and you will get this number. So it basically says your PMOS is bigger in size than NMOS. Okay, and each one of them has their own uses, has their own applications. I'll very soon tell you where this kind of waveforms or where this kind of buffers or inverters are used in a real circuit, in a real physical design circuit. So I'll come to that. So these two have their own applications. There is nothing called as good or bad. Everyone has got their own applications. So let's start with, let's look into the waveform. So this was the waveform, and this was the waveform for a device which was bigger than NMOS. So clearly, if you see, the shapes of the waveforms are same. If you see the shape of this one and the shape of this one, irrespective of the voltage levels at which they are switching, if you look into just the shape, they're almost the same. There are few glitches in this region and this region, and also over here as well, but the shape remains the same. So what does this tell us? This tells us that the CMOS inverter is a very robust device. Okay, there are certain parameters that will define the robustness of the CMOS, but this says that your CMOS, whenever your input is 0, this is your V in. Whenever your V in is 0, your output is high. Whenever your V in is high, your output is low. So this characteristics is being maintained across all kinds of CMOS inverter, across all sizes of CMOS inverter. So CMOS as a circuit itself is a very robust is a very robust device, and that's why CMOS logic is the one that is being widely used for any of the logic gate designing. Okay, so that brings us to the parameters that will define the robustness of the CMOS, and one of them is the switching threshold. Okay, for the first one is the switching threshold. Switching threshold means the point at which the device switches. So we are going to evaluate the static behavior of your CMOS, and we'll come up with some parameters like switching threshold, noise margin, and so on, that will define the robustness of your CMOS. So basically it will prove to us that CMOS inverter is the most widely logic used for building any of the logic gates, and why it is used, because the characteristics of your CMOS inverter is such that it becomes very useful for these devices to be used in building of any of the logics. And one such parameter that will define the robustness of your CMOS inverter is the switching threshold. Okay, so let's find out what is switching threshold. Switching threshold is a point where your V in is equal to V out. Okay, so it's a so basically, how do we derive it? We basically draw a line, a 45-degree line from this point till the end, and then identify the point at which your V in is equal to V out. Okay, so in this case, let's try to zoom in this one. If you look into this case, so this is the point where your PMOS is your V in is equal to V out. Let's zoom in even more. Okay, so this is the point where your V in is equal to V out in this case, and this particular point tends to be somewhere around 0.9 volts. Okay, so it says that for this particular device, your switching threshold, this is a point where your V in is equal to V out, and that point lies somewhere at the intersection of this one and this one. So it lies somewhere over here. If you zoom more into this area, it will be about 0.9. Okay, that's with this kind of this kind of device, where your WP is 0.375, and WP by LP is 1.5. And in the other case where you have another device, a bigger one, so in this case if you zoom into this area, the point roughly comes to 1.1.25 something. It's not exactly at the center. If you see this one, this point comes to roughly about 1.2. This is the point where your v in is equal to v out. So that's basically an area at which you see the switching threshold to be somewhere where your v is equal to v out. So this brings us to many conclusions over here. So this area that you see for your CMOS inverter is a very critical area, because your input is equal to output. That is first thing. Second thing, we have seen in the past that this is the area where your PMOS and NMOS both are in saturation region. Okay, it means both are kind of turned on. Okay, if both are turned on, there is a very high chances of leakage of leakage current. I'll talk about leakage current in a bit from now. So there is a high possibility that the current flows directly from power to ground. So in this area you see lot of current that is being flowing in this area. Since one of your devices is off, same thing with this area. In these two areas, since one of your devices are on or off, in this case your PMOS is off and NMOS is on. Sorry, your PMOS is on and NMOS is off. In this case your NMOS is on and PMOS is off. In that case, there is no direct current that is flowing from your power to ground. Okay, but in this area, this is a very critical area where you see lot of power that is getting, a lot of current that gets flowed from power to ground. Okay, so this is a kind of short circuit device. Okay, I'll talk about these concepts in a bit from now. Let's move on and look into the switching threshold values. So these are the switching thresholds for this inverter and for this inverter, and the values we just identified. One, in this case it was close to 1 volt, so it's 0.98, and this case it was not exactly at the center, but it is about 1.2 volts. Okay, so these are the areas in which your PMOS and NMOS both are in saturation region. So we had looked into the waveform that while deriving this particular waveform, we had looked into each and every points of this one, at what regions of operation is your PMOS and NMOS are in. So in this case we identified that your PMOS and NMOS are at saturation region. It means that they are kind of turned on in this area. Okay, and the reason they are turned on is because their gate voltage, I'll come to that point, the gate voltage almost crosses it's very much above the threshold region. Okay, so in this case this is the case where your V in is equal to V out. When you say V in is equal to V out, your gate voltage is equal to your drain voltage, which means VGS is very greater than your threshold voltage. Okay, so this is the conditions. Your VGS is equal to VDS. Okay, and also another point is, at this particular point, at this particular operating region condition, the currents that is flowing in this area, that's almost same. Only the directions will be different, but the currents that flow. So for example, if there is a current flow from this area, from PMOS to NMOS, and from this capacitor to the NMOS, the direction of the currents are different, but the values of the currents will be exactly the same. Okay, that's why we write at this particular area your VGS is equal to VDS. Okay, and your current has got an inverse direction. Your IDSP, the drain current of your PMOS, will be in this direction, and the drain current of your NMOS will be in this direction. So if you note the directions of the current at this node, your PMOS current in this way and your NMOS currents in this way, so the direction of the currents are inverse. And as a result of that, you see your IDSP is your negative IDSN. So we have the boundary conditions, we have the conditions at which your switching threshold will arrive. So your IDSP is equal to negative IDSN, your VG is equal to VDS, and we also know what is IDSP, what is IDSN. So the next part is to next work is to derive the value of VM. So basically we need to solve certain equations so that we can get an early validation or early value of VM by just having the values of WN by LN or WP by LV. So it's basically, we have these values and we need to calculate the VM, or vice versa. If we want to set a value of VM, what should be the value of WN by LN and WP by LP? So that's what we will be doing in the next video. So let's try to, since there are a lot of derivations involved and there will be a lot of analytical things that we'll be talking about, let's try to continue with the derivation of the switching threshold in the next video. Thank you.